Let's describe the physical features of a wave. Let's suppose I have this wave here. Okay, and we've talked already that the distance between two of the same features, so crest to crest, would be an example of the wavelength. Valley to valley would be an example of wavelength. And then even more carefully, any point, so let's say right here, right to the right of this crest, it's not this point here, but rather this point would be the wavelength. Because it's to the right of the crest, to the right of the crest. It has to be the exact same location and how it's moving. Okay, now the period is the time it takes to go through a point. So if I mark here as t equal 1, then, or t equals 0, and then I wait when this goes and gets to here, and I mark that as t equals 1, t1 minus t0 is the period. And so I'm going to just review that by just saying that the wave speed, okay, the wave speed is equal to that distance of a cycle over the time of a cycle. That's the period. Okay. Now something that's convenient is sometimes instead of counting how long it takes for a wave to travel, we can count how many times a wave passes in a second. And so I'm going to look at this spot here. Okay, not necessarily in the wave, but just at this location in space. And I start my watch, and I go for just 1 second. And I say, how many times did a crest pass by? And if I think of it that way, I'm counting the frequency. F equals frequency. Okay, counting the frequency of the waves, and it's related to the inverse of the period. Frequency equals 1 over the period. So if one wavelength passes by, so one cycle passes by, one wavelength passes by, then I have 1 per second. Okay, and the period would have been 1 second because it took me 1 second to count from this one to this one. Okay, so the frequency is inverse to the period. Another thing that's important is what's called the amplitude. So I drew this trying to represent some equilibrium line. So if this was a water wave out on the ocean, waves are caused by wind, and on a calm day, the water would rest flat along this line. This is where the water wants to be. Gravity's pulling it down, keeping it nice and flat. Okay, but when the wind picks up, it causes these waves to happen, and so it causes some wave to build up, causing some of the water to build up while taking away some of the water from one place, and it keeps doing that. Okay, the amount of water displaced from its equilibrium point. So this is again the equilibrium line. The maximum distance it gets displaced we call the amplitude. So that is of size A, or the amplitude, and this is also of size A, or the amplitude. A equals amplitude. Okay, and we can choose a positive or negative by actually drawing a coordinate system here, and we can call this D, displacement, the displacement of these particles from equilibrium. And so this would be a positive A if I chose up to be positive. Okay, I could do so by with my label and an arrow there. And then this could be right here. That could be negative A. So the amplitude's a positive number, but my wave can be anywhere from positive A to negative A for the motion, the displacement away from equilibrium. Now something that's really important is these terms, the wavelength, the period, the frequency, they're describing how the wave is traveling. That's the travel speed of this disturbance. But we're going to come up with a relationship that describes the position of the molecules at the surface. So what is the shape of this curve, this wave curve, at all points in space? And that's going to give us an equation for displacement, which is a position, but we're also going to find that it moves. And so like if I look at a water molecule right there, it's going to move up and down as this wave passes through it. And so that molecule will also have a velocity, but it's going to be a velocity up and down rather than traveling. And so we'll get an oscillatory velocity there associated with this oscillatory shape. So we'll go into that in greater detail in a later video, but what's important is recognize the difference between the displacement and the velocity associated with the displacement, the up and down motion, versus the velocity associated with the disturbance traveling, the wave speed.